Hello and welcome to another general chemistry video. Today we will be talking about module 11 and specifically how to figure out electronic configuration. Now, before I tell you about what electronic configuration is and how we find this, I need to bring to your attention several modifications that we have to do in order to help facilitate this process. One of these things is we have to move helium to sit next to hydrogen. Another of these things is that we have to number our periods within the periodic table. And finally, we have to split up the periodic table into the four different parts, the S, P, D, F block, right? So let's get started. What I'm actually going to do is I'm actually going to give you the electronic configuration for carbon, and hopefully you will be able to see the pattern, right? So the electronic configuration for carbon is 1s2, 2s2, and 2p2. And this is a ground state carbon, right? So if you notice that this electronic configuration has three separate parts, but each of these parts have a similar form that they follow. First of all, they have a coefficient, and this represents the energy level. Next, they have the block. I'll do B for block, which represents what block we're talking about. And finally, they have this exponent, which really is just talking about what position within the block that the element is found in. What do I mean by this? Well, look at this. First off, we start off at 1s2. So we had to go to the first block, or the first row, in the S block, and we have to go two spaces within it. Then it says go to the 2s2, second block, go to the S block, or second period, go to the S block, and go two spaces within that. And finally, 2p2, go to the second row, P block, and go 2p2. So notice there is a sort of pattern that you do have to follow, and it's really just following the atomic numbers within the periodic table. So that means to go left to right, left to right, left to right, left to right, left to right. Now remember, it's always beginning with the energy level, followed up by the block, and how many spaces within the block that we're talking about. However, there is a trick to this. When we're talking about the transition metals or the lanthanide and actinide series, we do have to do some modifications because their energy level does not directly line up with their period number. What do I mean by this? When we're talking about the transition metals, we had to subtract 1 from their period in order to find their energy level, and we had to do subtract 2 from the F block. So if we're talking about the vanadium, vanadium is in the fourth period, but even though it's in the fourth period, its energy level is on the third. Okay, well, just think of these as directions and you should be able to figure this out with a little bit of practice. And this is what we're going to do next. So I have a electronic configuration of some elements here on the bottom. Pause the video right now and try to see what this element is. Okay, so you should have at least tried this by now, or at least pause the videos and try this right now. But here is the electronic configuration. So remember that we go 1s1, 2, 2s2, 2p, 1, 2, 3, 4, 5, 6, and then 3s, 1, and then magnesium, right? So if you said that this electronic configuration is for ground state magnesium, you are completely correct. Now I keep saying something called the ground state, and why is this important? Well, let's look at what electronic configuration really means. When we're talking about electronic configuration, remember, we're not really talking about the proton, so the actual atom or the actual identity of the element does not matter. We're really just talking about the electrons. So when we're talking about this, let's take argon, for example. Argon has 18 electrons, right? But what other ions or elements have 18 electrons? Well, in ground state, argon's the only one. But when we're talking about electrons, chlorine minus and also K plus or potassium plus also have 18 electrons. And the fact that they all have the same number of electrons but different number of protons is what we call isoelectronic. So they are all isoelectronic, right? So just remember, when we're doing electron configuration, you have to add or subtract to the electronic configuration wherever you see fit, right? So just don't do it and don't completely blindly trust a periodic table, and you have to start thinking about it a little bit more. Now, there is one more thing that I have to go over before we'll get into practice problems, right? So this is exceptions to the atomic, or to the electronic configuration. Now let's take the group of chromium and the group of copper, and let's see what we think and what we suspect the electronic configuration would be. Well, we would suspect that we have Ar, 4s2, and then 3d, 4 or 9. Oops, 3d, 4 or 9. Now, wait a moment. What did I just do here? Well, this is what we call the shorthand notation. And the shorthand notation really just makes use of the fact that if we're filling up within, say, if we're filling up that chromium, it's already implied that everything that comes before chromium is already filled up. So all of this, instead of writing out 1s2, 2s2, 2b, all that stuff, we just substitute it with argon, right? And we use the nearest noble gas that's already been filled up in order to not just, and to substitute everything and not have to write all of that. So just remember, you can also do this shorthand notation, and this does come in handy when you're talking about these lower elements, kind of like iodine, so you don't have to write every single one of them. Now let's continue though. For chromium and for the copper series, we expect something to look like this. We expect the electronic configuration to look like this. Now, you wouldn't be wrong in thinking this, but however, let's visually imply this, or let's visually express this using the orbital box diagrams. So if you see the chromium orbital box diagram looks something like this, remember we have the 2s12 and then the 3d4/9. Now there is something that you notice, that if we follow Hund's rule, there is an open box, right? There's always going to be an open box at the lower level, even though there's a full box at the upper level. So really what's going to happen is this electron, let's actually do this in another color. This electron will move from here to go over here. Same thing here. This electron will move from here to go over here. So just remember, if it's in the chromium, this actually makes our electronic configuration for chromium actually going to be Ar, 4s1, 3d5, and then Cu, if it's copper, Ar, 4s1, 3d10, right? Because it really wants this lower energy filled up as possible if it can. All right, so that goes over electronic configuration. Now it is time for you to practice. Here I have some practice problems. Pause the video right now and see if you can give me the full electronic configuration for gold, bromine, the bromine ion, francium, sulfur, cobalt, and the rubidium ion. So pause the video right now and give me that electronic configuration. Okay, well, you should have already, at this time, you should have already have your answers, and if not, please pause the video right now. You do need the practice. So, what are the answers? I'm trying to find it. Here they are. So, pause the video right now and go check out your answers. Gold looks like that. Sulfur looks like that. The cobalt looks like that. The bromine ion looks like that. The rubidium ion, oh, my bad. So, the bromine ion should not actually be the short one. The rubidium ion looks like this, and the francium ion looks like that. All right, so with that video, or with that, everything is done. We will see you guys in the next video.